All right, hello, welcome back to another Math Counts meeting. Today we're continuing the last few problems of 2014 national or 2012 nationals, sorry, and we are on team number 9. A solid cube is formed from 125 unit cubes. A set of unit cubes will be removed, leaving behind a smaller solid cube. In how many ways can this be done? For example, there are 8 ways to remove 61 unit cubes from the original 5 by 5 by 5 cube to leave behind a cube with edges of 4 units. Okay, so basically what we have here is, we have a solid cube from 125 unit cubes, right? 125 cube rooted is 5, right? So that means we're forming a cube with a side length of 5, and it's composed of like a bunch of unit cubes, right? So basically, it's just a cube that has a side length of 5, and then we want to find how many ways we can take away cubes so that we are left with another cube, and the cube that we're left with, it can be of any dimension. When you just think of that, it seems kind of hard, but you can just count it based on um, how many like different cubes you can have in this cube. So if we're looking at 4 by 4 by 4, the number of ways for us to remove cubes and get that cube is just going to be the number of cubes, the number of 4 by 4 by 4 cubes that we can fit in our 5 by 5 by 5 cube. And that is because, for every 4 by 4 by 4 cube that exists in our 5 by 5 by 5 cube, there's going to be, you know, there's going to be one way to remove the cubes to get to that cube, right? So then we're just counting the number of 4 by 4 by 4 cubes in our 5 by 5 by 5 cube, or for that case. So then it's easier to think of. So then we can change this problem to just counting how many cubes of any size exist in our 5 by 5 by 5 cube. So then you need to think about how you can do that. And with the 4 by 4 by 4 case, or we can think of casework at the start. So start with counting how many 4 by 4 by 4 cubes you can fit in here. Um, and that's pretty easy to see. You're just gonna have one possible 4 by 4 by 4 cube on every vertice of the 5 by 5 by 5 cube, and there are 8 vertices of the 5 by 5 by 5 cube. So then you're just gonna have 8 4 by 4 by 4s. I'm just gonna say 4s because I don't want to write it all out. Okay, and then the 3 by 3 by 3 cubes, it's not as easy as the 4 by 4 by 4 cubes. Um, but there's a better way you can think of to counting, how many of a certain size cube fits in the 5 by 5 by 5 cube. And that's like you think of where the like the vertex cube of your smaller cube, you think of where that can be placed in your larger cube. Um, this is kind of hard to explain because you have to kind of visualize it in your head. But so um, we're dealing with the 3 by 3 by 3 case. So imagine a 3 by 3 by 3 cube inside of your head. So it looks like this, right? Now think of where this cube at like the bottom left here. Think of where this unit cube can be placed in our larger 5 by 5 by 5 cube. It obviously can't be placed like right here, right? Because then because this is our lower left cube on our 3 by 3 by 3, then our 3 by 3 by 3 would not be inside of our 5 by 5 by 5. So then where can this go? This can go in a bottom left 3 by 3 by 3 cube inside of our 5 by 5 by 5 cube. Um, so it looks like this. So, um, basically, like our lower our lower left 3 by 3 by 3 chunk of our 5 by 5 by 5, that is where this unit cube can be placed, right? Because on all of these, this is gonna be the third unit cube on here, right? There are gonna be 5 unit cubes on here, and if it is on this, then we're gonna have 2 additional spaces on this right here to fit in this length of our unit cube, right? And so basically, we have to be confined within this 3 by 3 by 3 because if we are any more than 3 um of length when we put this cube, then we're not going to have enough space to put like either one of these sides, right? I mean, you can also think of this like, you can start by looking at one dimensional, right? So if you have a length of 5 line and you're putting a length of 3 line into your length of 5 line, then where your unit length of 1, where that can be placed is going to be inside of a length of 3, right? You know, you can also picture it like this. If I need to take 3 lengths from here, where can I place my leftmost length? Well, it's either going to be this, this, or this. So I can only place it in the 3 leftmost positions. And when you extend it to 3 dimensions, it's just like that, but in every dimension, right? So then we have to put our, leftmost unit cube here in this 3 by 3 by 3 cube. And I'm not sure how well I can explain this because this is a fairly visual thing. So if you guys don't get that, just hello. Is the recording still on?
Oh, yeah.
Okay. So yeah, we can just count how many ways we can put this leftmost unit cube, left bottommost unit cube, and that will also be the number 3 by 3 by 3 cubes we can have. And like I said, where we can place it is this is in this 3 by 3 by 3 chunk, right, which consists of 27 unit cubes. So then um, we have 27 places to put our unit cubes. So then we have 27 3 by 3 by 3s in our 5 by 5 by 5. So then we have 27 threes. And then for our 2 by 2 by 2, we can do the same thing. And this time it's gonna be a 4 by 4 by 4 inside of our 5 by 5 by 5, right? We're making our cube one smaller, so then our left bottommost unit cube can be an extended one position in any direction. And then we count how many unit cubes are in that 4 by 4 by 4, which is just going to be 4 cubed, which is just going to be 64. And then our 1 cube, we can just think of how many 1 unit cubes are in our 5 by 5 by 5, and it's easy to see that's just going to be 5 cubed, which is 125. And we can also use our same thing we've been using, and you would also see that it's 5 by 5 by 5, and then it's also 5 cubed. And we can see we have a trend here where this is 2 cubed, this is 3 cubed, this is 4 cubed, this is 5 cubed. So for all of these, whatever length of cube that we're looking at, if that is x, then the number of cubes of that we can put in our 5 by 5 by 5 is going to be it's going to be 6 minus x cubed. Okay, so now we just add all of these together. It's going to be 8, 27, 64, 125, and you get 224, and that is our answer. Anything you want to say on that, Bill?
Yes, like what Austin did. Austin went from a 1D to 3D, but this also exists in 2D. So if you have squares, you can think of the vertices.
Yeah. Okay. Our last problem is, oh yeah, did you want to say something?
Oh no.
Okay. Our last problem is, what is the slope of the line that bisects the acute angle formed by y equals 4/3 x and y equals 12/5 x? Express your answer as a common fraction. Okay, so basically we have two lines. This is of slope 12/5 and this is of slope 4/3. And we want to find, this is an angle here, and we want to find the slope of the line that bisects this. So so this is a target, or this is a team problem, which means that you can use calculators, and you can also use CAS calculators, TIs, and whatever, and so on the actual test, you should use these resources whenever you can, right? You just want to complete all of the problems as accurately and as quickly as possible. So because this is a team problem, on the actual test, everyone should just, whip out calculators for this problem. Because with calculators, this problem is going to be very fast and much faster than if you worked it out with no calculators. So yeah, because you can use calculators on this, just use it, right? Then you can do it more accurately and more quickly. And then, so how do you do this with calculators? Well, to find the angle of a line when you have its slope, well, all you have to do is set up a triangle. So, let's say our slope, let's just use our 4/3 line for the slope line. This means that we go up 4 every time we go right 3. And then this triangle is going to be a right triangle, and our hypotenuse, the length that we go on the line is going to be 5. And then, and then we want to find what this angle is right here. And then on this angle, we can just use trig, right? We can just say that this angle, we can call that alpha. Alpha is going to equal the tangent of 4/3. I mean, that's just basic trig, right? And you know, I took this as you go right 3 and up 4, but more I don't know, more technically correct will be saying like you go 3 times x in any direction, And if you do that, then you go forward, or not any direction, in the rightward direction, and then you would have to go 4 times x in the upward direction. That's what our 4/3 slope is saying. So then alpha more generally would be the tangent of 4x over 3x, but you could see that the x cancels, so that it's always going to be the tangent of 4/3. So then, if you have any line, then the angle it makes with the x-axis is just going to be tangent of the slope. So then what you can do is you can find, with a calculator, you can very easily find, what this angle is on the 4/3 line. You can find what this angle is on the 12/5 line. Then you could subtract the two angles. Then you get what this middle angle is. Then you could half it. Then you could add it to your 4/3 angle, and then you could arctangent, right? You can arctangent it to get what the slope of this middle line or the bisector line is, because what I just did is going to give you the angle from this bisector line to the x-axis, and then we just said that that angle is going to be the tangent of the slope, so we can take the arctangent of it to get what the slope is. Okay. So let me just put that into my calculator just to make sure that it works. So we're going to take the tangent of 12/5. We're going to subtract the tangent of 4/3. That's going to give us our middle angle. We can half it. And then we add it to tangent of 4/3. Okay. And now we're going to arctangent it. I got 1.0144. Wait, I don't think that's correct.
I got 1.75. So what did you do there? Is that supposed to be a 6 or 5?
A 5. I think I put 5. Okay, it's going to be tangent 12/5 minus tangent 4/3, right?
No,
No.
it should be arctangent 4/3 plus arctangent. It should be a
Oh, no,
tangent
I'm
parentheses
bad.
arctangent 4/3 plus
No,
arctangent
okay, yeah, yeah,
12/5
yeah,
over
yeah,
2.
yeah, yeah, yeah. Yeah, I messed this up really badly. But it's not that the angle is tangent of the 4/3, but the tangent of the angle is gonna be 4/3. So actually it's gonna be tangent of your angle is gonna be your slope. Or you can have your angle as arctangent of your slope. That was just a mess up by me. I don't know why I said that. But yeah, I mean, that's just basic trick. You always do your trick on your angles. Um, okay, but yeah, that was my mistake. So then on this, what you would do, actually you would take the arctangents of the slope to find the angle. So then you would do, arctan of 12/5 minus arctan of 4/3, and that will get you what the middle angle is. And then you divide it by 2. That will give you like the half of this angle, and you can add it to the angle of 4/3, which is arctan of 4/3. And that will give us the angle of our bisector line. You can also think of it as just the average of the two angles of our line. So then it would just be arctangent of 12/5 plus arctangent of 4/3 over 2. And we can also see that our before expression, if you combine this into there, you would also get this expression. Okay, but yeah, you arc tangent on the slopes, not tangent. Okay, so let me do that. Um, Wait, what? I got 1.05165. I'm doing arctangent of 12/5. Oh, I'm in radians. Wait.
That shouldn't make a difference. Did you tangent
Uh,
the whole thing? Did you put the whole thing in tangent?
oh yeah, yeah. Okay. No, yeah. No, yeah. No, wait. Okay. Wait, what? Okay, there we go. Okay, yeah. So this is gonna be the angle of our bisector line, and um when you have the angle of the line and you want to get its slope, you're gonna take the tangent of it, right? So then you take the tangent of this, and then I finally got 1.75 from the calculator, and then um, you know you can say that this is probably gonna be 7/4 as your answer, and that is your answer. Um, so on the actual test, um, I mean, the best strategy would probably just to do this because doing it with a calculator is probably going to take much less time than if you're going to work it by hand. But I'm also going to work this problem by hand because um, just for more concepts, and this kind of problem can also show up on like Sprint or something, and you're gonna want to know how to do it. It's also a good trig problem. So I'm gonna show how to do it by hand, and basically you're doing like the same thing, but you're gonna have to work this stuff out with hand trig stuff. So um, so we're gonna have our 12/5 line. We're gonna have our 4/3 line. That's not to scale at all, but yeah. Okay, let's call the angle on our 4/3 line alpha and the angle on our 12/5 line beta. And the angle of the central line is going to be, like we said before, it's going to be alpha plus beta over 2. And we want the slope of that line, so we're going to want the tangent of alpha plus beta over 2. And with alpha and beta, we can get the basic trig of these, right? We can make a 3, 4, 5 on alpha, and we can get the basic trig, cosine, sine, and tangent. So basically, our mission is to convert this expression with trig identities and stuff into a expression that only has basic trig of alpha and beta. So convert it into just like just trig with just alpha and stuff. So how are you going to do that? Well, there's something called half angle identities, and basically that's whenever you have like, say like cosine of x over 2, but you want to put this in only terms of cosine of x because you only have cosine of x or something, and this is very useful, so you're going to want to know this. So I am going to derive the half angle formula for sine and cosine. So we know that cosine of, let's say, A and B, A plus B, this is going to equal cosine of A times cosine of B, minus sine of A times sine of B. And this is just a basic trig identity. If you don't know this identity, um, honestly, I would just say you should probably memorize it. The other one with sine is sine of A plus B equals sine of A cosine of B plus sine of B cosine of A. These are basic trig formulas, and they're very useful. So if you don't know them, I would say you should get to know them. And then what you can do instead of having A and B, you can have it as the same thing. So you can say A is X and B is X. So then you have cosine of X plus X, but then you can just simplify that into cosine of 2X. And then your right side is going to be cosine of X times cosine of X, right? Which is just going to be cosine squared of X. And you're also going to have minus sine of X times sine of X. So that's going to be sine squared of X. So now we have that cosine of 2x equals cosine squared of x minus sine squared of x. Now this is called the double angle identity, and it's useful when you have double of an angle that you have like knowledge about their basic trig. But this is not exactly what we want, right? We want the half angle identity. And why we want the half angle identity is because we have alpha plus beta over 2. We have half of the angles, that we're familiar with. So we want to use the half angle identity, not the double angle identity, right? If we use the double angle identity on this, then we're going to have alpha plus beta over 4 on our like basic trig stuff. And we're not familiar with that, and that's not going to be a great pathway to go. But we can actually derive the half angle identity from this double angle identity. And how we're going to use that is we're going to use another identity, and it's sine squared of x plus cosine squared of x equals 1. This is another very basic trig formula. If you don't know it, you should get to know it. I mean, I feel like this is pretty easy to memorize, but it's also, you can also think of it as, you can also think of it as like a unit circle stuff, and like the radius is always 1, and so sine squared of x plus cosine squared of x is always going to equal 1. And with this, you can say sine squared of x equals 1 minus cosine squared of x, and you can say cosine squared of x is equal to 1 minus sine squared of x. And you can see that we have sine squared of x and cosine squared of x here. What we can do is we can make substitutions into these, and we get the other trig squared, and then basically we can put this into just one like type of trigonometric function, and that's going to help us out. So we can make both of these substitutions, and so let me make the sine squared of x substitution right here, and I'll make the cosine squared of x substitution right here. So if we make the sine squared of x substitution, then we're going to have 2 times cosine squared of x minus 1. And the cosine squared of x substitution, we're going to have 1 minus 2 sine squared of x. And then what we can do with this is we can solve for cosine of x, right? If we solve for cosine of x, we're going to have cosine of 2x plus 1 over 2 rooted. And this is going to equal cosine of x. You can also do it to here. So if we do it to here, we're going to have 1 minus cosine of 2x over 2 rooted is sine of x. Now here, we have the trig of x, and we're putting it in the trig of 2 times x. you can substitute x as y over 2 or something. So then we have cosine of y over 2 is the root of cosine of y plus 1 over 2. So then you can easily see that we just derived our half angle identity here, right? It's that we have half of the angle we are familiar about. We're putting it into a common trig, and this angle we do know about. So yeah, this is the half angle identity for cosine. And then for sine, we can see that it's just going to be with this, except the cosine is negative. So yeah, these are our half angle identities. If this was kind of or if you didn't get this, you can always just let us know, and we can try to explain it further. But there's also a lot of resources on this, I bet, like elsewhere, probably like Khan Academy videos or whatever. So you can also watch those for like derivation of half angle or something. And yeah, you can also do that. But yeah, so now that we have these, we can apply it to our thing. And generally, if you're doing competition math, you're not going to want to derive these on the test, right? You're not going to have that much time. So for competition math, you're probably just going to want to memorize these, so you can know it at the top of your head, and you can just directly apply it to not waste that much time. Okay, so we have tangent of alpha plus beta over 2. And we can say that this is, sine of alpha plus beta over 2 over cosine of alpha plus beta over 2, right? This is just like the definition of tangent. And now that we derive the half angle identities, we can apply it on here. And this is going to be good because we're changing our alpha plus beta over 2 into alpha plus beta. And that is more closer to what we want, which is just the trigs of just alpha and just beta. And if we have the trigs of alpha plus beta, we're pretty much already there, because we can just then use the trig of a plus b identities to get the trig of a and b individually. And yeah, we can just use that. So basically we can already see the path that we're taking all the way to the end. Okay, so now we're going to apply our half angle identity. So sine of alpha plus beta over 2, it's like our y here is alpha plus beta. So then this is going to equal 1 minus cosine of alpha plus beta over 2. And then this is going to equal the root of cosine of alpha plus beta plus 1 over 2. We could cancel out the over root 2's, and then we have the roots of 1 minus cosine of alpha plus beta over cosine of alpha plus beta plus 1. So now we can use this identity. We have cosine of alpha plus beta, and we want the individual trigs of alpha and beta. We can use this to get the individual trigs of a and b and stuff, right? So if we apply that, then we're going to get that this all equals 1 minus the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. And then, we're just going to make the same substitution into this one. And then this is our expression. Now this is good because now we've written what we wanted, which was, the trig of a, complicated angle that we couldn't really say anything about. Now we put it into simple trigs of angles that we do know about. So now we just need to find what these values are, and we can plug it in, and we can find what we wanted. And so let's just find these common angle trigs first. So on alpha is on our 3, 4, 5, right? So that means cosine of alpha is going to equal 3/5, and sine of alpha is going to equal 4/5. And then our beta was on our 12 and 5. So then, this is also a Pythagorean triple. So then that is going to be 13. So then cosine of beta is going to be 5/13, and sine of beta is going to be 12/13. And I'm just going to find what this expression is once, and I'm also going to apply it into here. So, whoops. So cosine of alpha is 3/5. Cosine of beta is 5/13. Sine of alpha is 4/5. Sine of beta is 12/13. And then this is going to be 3/13 minus 48/65. And if you simplify that, you're going to get you should get -33/65. So this is that stuff, and we can just put it into both of them. So then we have 1 plus 33/65 over 1 minus 33/65. And then if you solve that, and you take the root, then you get that this is going to be exactly 7/4. And that is how you can work this by hand. But clearly you can see, I already knew how to do it, and it took me significantly longer than if I would just use a calculator. So again, if you can use a calculator on this, where you're allowed to use a calculator and you could do it much faster, than just use a calculator. But if you don't have a calculator and you have to work it by hand, then just work it by hand. Like on this problem, even if you could use a calculator, when you're looking at it, by yourself, not on the actual test, it's good anyway to know how to work it by hand, because they can also ask, a similar question with similar concepts to this question on, Sprint, where you can't have calculators. So, it's also good to know the concepts just for doing it by hand. Okay, anything you want to say there, Bill?
I think you did it pretty well.
Okay. So this is the end of 2012 nationals, or 2012, I believe. Anyway, now we're going to do some math counts trainers problems. We're just going to showcase some math counts trainer. Should we also have like a drawing thing next to it?
Do you think we should?
I'm not sure.
Do you think we'll need to?
I'm not sure.
We could just do it.
We can try it without one first.
Yeah, we can try without. See how that goes.
Okay. Math counts trainer. Okay. Oh, what the heck? Okay. Okay, you can see my screen, right?
Yes.
Okay. Um, okay, so we're just gonna showcase some Math Counts Trainer. Math Counts Trainer is like it's a it so it's a good training website for math counts. Like it gives you math counts problems and you can get to harder math counts problems by doing uh by doing easier math counts problems. So you can see on this count I've gone to state, so now we can do some state problems. And I mean this is just good for like going through math counts problems like quickly and stuff. And it also gives you the solutions to the problems. So like at the end. So that's also pretty nice. Okay. A standard six-sided die was rolled repeatedly. The frequency table below shows how many times each number was rolled. What is the mean of the 20 numbers rolled? Express your answer as a decimal to the nearest hundred. Okay, here you can just add up all the values of the rolls. So we had four number ones, so we're gonna multiply 4 by 1, and then we have four number twos, so we're gonna multiply 4 by 2. We had three threes, so we're gonna multiply 3 by 3, and we're just gonna do that with all the things to get the total value of all of the rolls. And you want that because you're finding the mean. You just divide that by all of the number of rolls, which is 20, and then you should get 3.25. And that's correct. Very cool. Um, do you think you read these problems?
Yeah, that's fine.
Okay.
Jack and Jill drove in separate cars to their favorite hill, leaving from the same place at the same time. Jill drove 20% faster than Jack and arrived half an hour earlier. How many hours did Jack drive? Okay,
Okay.
so she drove 20% faster.
So her speed is going to be multiplied by 1.2, right?
Right, yes. So the time would be
Right. The time is going to be distance over speed. The distance is the
yes.
same. So then her time is going to be 1 over 1.2 um, faster. Um, well, I mean, okay, like if you say x is, let's just say x is Jack's speed. If x is Jack's speed, then Jill's speed is 1.2 times x. Then the time it took for Jack is 1 over x. Time it took for Jill is 1 over 1.2 um, times x. Then you could subtract their times. So it's going to be, wait, I feel like you don't get calculators.
Yeah, probably not.
One, okay. 1.2 is just 6/5. So then, okay, I got 1 over 6x. So I got that their difference is time is 1 over 6x. And it says that this is, they arrived half an hour earlier. So I can equate this to equal 1/2 if my units are in hours. So then I can solve for my x, and I get that it equals 1/3, I think. So then Jack's speed was 1/3. Um, wait. Um, okay. Okay. So Jack's speed was 1/3. And then the time it took for Jack is 1/x, right? So then the number of hours that Jack drove is gonna be 1/1/3, which should be 3. Let's
Okay,
go.
so I think my solution is kind of different from yours.
Sure.
Okay, so think about it this way. When Jack arrived, Jill is half an hour behind, right?
Or the other way around, right?
Oh right, my bad. So when Jill arrived, Jill is half an hour ahead. So let's say, how do I say this? Um, let's say Jack's speed is X, right?
Yeah.
And then Jill's speed would then be 1.2x, right?
Yeah.
And then, so by the time Jill arrived, Jill would have pulled out a 0.5x lead over Jack. And each
Um,
hour, Jill increases the lead from Jack by 0.2x. So from that, we can find that Jill drove for
okay.
2.5 hours, and then Jack drove for 3 hours.
Yeah. That's also a good way to do it. In a 10-kilometer race, each runner runs 5 kilometers to point P and returns to the start by the same route. Ian runs 4 kilometers faster than Sean. Ian runs to point P, turns around, and meets Sean 4 kilometers from the start. Assume that Ian and Sean each maintain a constant speed and start at the same time. What is Sean's time in minutes for running the 10 kilometers? Um,
Okay.
so Ian ran 6 kilometers and Sean ran 4 kilometers, right?
Yep. Ian ran. Yeah. Yes.
Okay. So um,
So it took Ian half an hour to run 6 kilometers.
did it say that?
Well, from what we know, we can find out that it took Ian half an hour to run the 6 kilometers, right?
Oh, okay. Oh, he got a 2 kilometer lead.
Yes. And he
So
runs
then
four
he
kilometers
ran
per
six
hour faster.
kilometers in 30 minutes.
Yes.
So then he runs 12 in 1 hour. So if he runs 12 in 1 hour, then Sean runs 8 in 1 hour. So then Sean's time should be 10/8, which will be 5/4 or 5/4 hours. So then it's 5 times 15, which is 75. Can you hear the music?
Sort of.
Sort of.
Yeah.
Two sides of a triangle have lengths 23 and 53. The third side has length of n squared, where n is positive integer. How many possible values are there for n?
Ooh.
Okay. First thing about like minimums not considering Yeah.
Yeah.
The integer square first.
Minimums and maximum.
So minimum is going to be 31. Maximum is going to be 75.
Yeah, 75.
Or 76 is the strict bound.
Yeah.
Okay, and then find the squares. So it's going to be 36 to 64. Then that's 6 to 8. So then that's 3. Let's go. Emma and Ed walk into a room containing 30 assembled torques and enough pieces to assemble 100 more torques. A torque takes 8 minutes to assemble and 10 minutes to disassemble. If Emma starts assembling torques and Ed begins disassembling the ones that were already made, and they both continue to work until there are exactly 35 assembled torques in the room and no partially assembled or disassembled torques, how many minutes will Emma have worked? Okay,
Exactly 35. Okay.
every 40 minutes, there should be one more assembled. So then it should just be 40
Yeah.
times 5.
Yeah. So 200.
Let's go. See, I can just see, every 40 minutes,
Mhm.
one more is going to be assembled. And if you already have 30 assembled and we're going to get 35, we need to assemble 5 more. So then it's just going to be 40 times 5, which is 200. You can also check out their solution. I think it's a little bit different. What is the least possible denominator of a common fraction that lies strictly between 1/3 and 1/2?
The least.
Well, it can't be 2 or 3.
Yeah, 5, I think. Yeah, it would be 5. Because for 4, it would have to be 1/4, which is too low, or 2/4, which is on 1/2.
Yeah.
So it have to be 5, 2/5.
Does 2/5 work?
2/5, yeah. I'm pretty sure 2/5 works.
It's obviously lower than 1/2.
Yeah, 2/5 is higher than
it
1/3.
works.
It's higher than 1/3.
So for this one, I would say you just like check, you go down and you check each one. Ooh. An urn contains marbles of 4 colors: red, yellow, blue, and green. All but 45 of the marbles are red, all but 45 are yellow, all but 45 are blue, and all but 60 are green. How many of the marbles are green?
Interesting. So there are 45 non-red. Wait, all but 45 of the marbles are red. 45 non-red,
Okay, what if
45
you called
45 non-blue, 60 non-gray. Okay. So, red, yellow, and blue.
Yeah, I'm gonna try 5. Okay.
Okay.
I didn't do it like that, but okay, I said red, yellow, and blue. They're all the same, right? They all
Yes.
have the same conditions.
Yes.
I called that X.
Mm-hmm.
So X plus 45 is gonna be the total.
Yes.
So X
Right, I was
plus
just
45
yeah, okay.
minus 60 is gonna be green. So green is X minus 15.
Mm-hmm.
Now, another way to get the total is if you sum X minus 15 and the 3 X's, right?
Yeah.
So then that's 4X minus 15, and we said before that the total was also X plus 45. And then you equal that and you get 5. He, their way is also a good way, I would say. Um, the first term of a given sequence is 1, and each successive term is the sum of all the previous terms of the sequence. What is the value of the first term which exceeds 5,000?
Okay. All of the previous terms. So it will be like 1, 1,
1, 2, 4.
2, 4.
Well, it's just gonna keep doubling.
Yeah.
That's easy peasy. It's just gonna be 40. It's gonna be
4096.
10242048. Okay, yeah, okay.
4096 and it's
409
80
8192.
8192.
Yep. 40 problems. Oh, I didn't know I was on that video streak. Okay. What is the measure of the smaller angle between the hands of a 12-hour clock at 12:25 p.m.? Express your answer as a decimal to the nearest time. Me and Tony made a
What?
UIL function just for this.
Just for this? Yeah. Oh, I remember this. Well, are you going to use it?
I'm gonna use it just to see if it works, but
Measure
we
the
should also
smaller angle
do it.
between the small hands and toe. This isn't that hard on this like this one isn't that hard.
Well, it shouldn't
One is at one.
really.
What? Sorry, what?
It, uh, it, uh, it shouldn't really. I mean, these problems aren't that hard.
Yeah.
I mean, it's just to save a little bit of time. I mean, UIL is a lot needing on time.
Yeah.
Um, it should be the hour hand should be 25/12, right? Minutes. That's where it is.
It should be what?
It should be at 25/12 minutes.
25/12. Yeah, yes.
Okay. So then you can subtract to get the minutes, and you multiply that by 6. Um, Multiply by 6. I got 137.5. Okay, let's see if the calculator works. I think I need to put it in degrees. I forgot where I put like all my functions though. Like
Good
in
job.
which
You made functions, but you don't know how to use them.
I made name, like I put them into sections and I made names of the sections.
hmm
I think it could be other geometry. Yeah, it's in the other geometry. Wait, but you also need to know the parameters.
Yeah.
Okay, it says it's hour and then
Doesn't
minute.
CAS have like a thing where it tells you the parameters? Like you can.
Yeah, you can do that, but some of them we didn't put like forgot, or like Tony
Well,
didn't put them on his
who's
at
to
the
blame
beginning.
for that?
Okay. What? It says 222.5. Uh,
Good job.
Wait, does it need to put hour 0?
Okay, hold on. 222.5. That's just the bigger angle compared to 137.5, right?
Oh, yeah.
Yeah.
When you put 0, it is a small angle. Okay. A liter of liquid contains 1% salt. How many liters of pure water must be added to make the new solution only 0.25% salt? Well, you can say we have, 1% salt of a liter of liquid, then we're gonna have 10 milliliters of salt. Then you can think of, you know, how many liters of water am I gonna have to 10 milliliters of salt, so that it's 0.25% salt? Well, it's gonna be 10 over x, or it's gonna be 0.01 over x equals 0.0025. And then you just do that, and you can see that your x needs to be 4. So then you need to add 3 more liters of liquid. But you can also think of this as, you're making the salt ratio decrease by fourfold. And, salt to water, uh, and like if you're decreasing the salt ratio by fourfold, you need to increase the water ratio by fourfold. So then, you have 1 liter of liquid, you need to get 4 liters of liquid. So then you need to add 3. Okay. Quadrilateral ABCD is a parallelogram. If the measure of angle A is 62 degrees and the measure of angle ADB is 75 degrees, what is the measure of angle ADC in degrees?
Angle AB. Measure of angle A. Well, if A is 62 degrees, then
Yeah,
ADC
ADC,
has to be
ADC. Okay.
118 degrees, right?
Yeah. And then you're just gonna.
Wait, isn't that it?
Oh wait, that's it.
Yeah. They gave us extra information, I think.
Yeah.
Extra information.
Okay. Yeah. Yeah. If you draw it out, and you know that two angles like two angles of a parallelogram, they have to be supplementary or adjacent. Like the adjacent angles of a parallelogram have to be supplementary. Just use that. Asha adds all the odd integers from 1 through 101 inclusive, and then subtracts all the even integers in that same range from her sum. What result does she obtain? Okay. If you're adding the odd integers, subtracting even integers, you're just gonna have ones everywhere. So you can pair up like 2, 3, 4, 5, all the way to 100, 101. And that's all gonna give you differences of 1, and you're gonna be left with a 1. So you need to think of how many pairs you can make. That's gonna be 101 minus 1 over 2. So you can make 500 pairs, or 50 pairs, and you have your initial 1. So then it's gonna be 51, or it should. Let's go. Or yeah, or you can pair it up like that and then have 101 at the end. You can also do that. Raymond sells 2 enchiladas and 3 tacos for 250, and he sells 3 enchiladas and 2 tacos for 270. Assuming a fixed price per item, what is the cost in dollars of 3 enchiladas, 4 tacos? Okay, just use the sum equations on this. Okay, I got 3.54. Sorry, my parents came in.
Okay,
Okay.
that's fine.
I got 3.54. It's just system of equations it should
Yeah.
be.
Yep. Solving system equation. What is the value of C?
Just I don't know.
So
Have
yeah,
we seen this exact thing before?
yeah, add it all up, I guess. Add it all up. Oh, actually, yeah, just add it all. So that's 320, 404 divided. Ooh, 404 divided by 5? That's not nice.
404 divided by 4.
4. How is it? Oh, it is 4. My bad. That's my bad. This is 101. And then we're looking at the one without
Minus
C,
82.
so 82. Yeah. 101 minus 82, that's
19?
19. Yep.
Oh, yeah. Right triangle ABC with legs AB is 3 and CB is 4 is rotated about one of its legs. What is the greatest possible number of cubic centimeters in the volume of the resulting solid? Express your answer to the nearest whole number. Um, would it not? Would, wouldn't it not matter what leg you choose?
Oh, the Great Bomb?
Like
I feel like it
rotating
would.
about a leg?
Yeah, I
Does
feel like
that
it
mean
would.
like? Does that mean like rotating it like 3D about it?
I think, yeah. So there's
But
something
aren't
like,
you rotating the
yeah.
same area of face through the same angle?
Well, but you would have to end up multiplying by the, what? The circumference of it, of like the circle thing, right?
Um, the circumference of the circle thing. Like how would you find the volume of it?
I think you would be able to get two different volumes from this, wouldn't you?
If you rotate it about one of the legs,
Uh-huh.
you just have
Cone.
um a cone.
Hmm. But you can have two different cones.
Are they
You do get two different cones depending on which leg you choose.
why? I don't know. Like um I guess it doesn't matter like what leg you rotate it on. Like because like you can rotate some farther and that would give like a larger volume.
Yeah.
Um,
Because if you rotate it, one of them is going to be like the the radius, one of them is going to be the height. The radius is squared, the height is not squared. So if you switch the radius and the height, you're going to get a different result.
how would you get the volume of the like if you rotate it by 5 though?
Well, 5 is not a leg, right? 5 is the hypotenuse.
Oh, what? Oh, I did not realize it just had line. So then it's
Oh
just
wait, I
gonna
misread
be
the question. It's asking for the greatest possible number of weight. Then that makes sense. I thought it was just asking for the volume. I was like, wait. No, it's asking for the greatest number. Okay.
Oh,
I
okay.
misread the problem.
So one of them is 12 pi, and then the other is 16 pi, I think. The nearest whole number. So you need a calculator,
Ooh.
right? Unless
You could just like approximate with like 3.14. That's not
I
that
guess,
bad.
I guess, I guess.
3.14 is like probably more than accurate for if you're approximating to whole numbers.
Yeah, I mean, you can also just you can also like see that, right?
Yeah.
Like, you know.
Yeah.
Oh, it's
It
8:01.
is 8:01.
Okay, we can just stop here.
Okay.
All right. Thank you for coming to our